Hello, everyone. Welcome again to this series, which is going on machine learning fundamentals. And we are on a very critical stage where we had discussed, in fact, earlier random forest classifier and related things. And today we are going to discuss some very important aspects of machine learning and those which are related to, in fact, the model, improving the machine learning model by different techniques. And definitely, when it comes to machine learning, it's not just about training the model or implementing it on a specific use case, but at the same time, you should be knowing techniques so that you can just improve. I was pointing it out last time uh, in one of the episodes that even if we are having a very little upliftment in the performance of a machine learning model, it is having a huge implication actually to the field or the domain in which that particular model is implemented. So, having said that, there are certain techniques which can, in fact, improve the overall machine learning model and its performance in various aspects. So, some of those aspects we have discussed earlier as well, and a few of those aspects will be the topic of discussion today. So let me just directly go to this validation, tuning, and reliability. These are some of the aspects which are very important as far as machine learning is concerned. We have seen that you are training a model. We have seen that in random forest. We have seen that in decision trees. We train a model. We are in fact calculating with some performance metrics. We have just evaluated that what is the performance of a particular machine learning model. But we realistically need to know that whether a particular model is performing well or not. So, how that is going to happen? This is the module which will be, in fact, giving us that we'll be able to ascertain how a particular machine learning model is performing. It is not just a coincidence or just a lucky go, or that it is happening that you are getting the results which are better, but it is genuinely the performance, the realistic performance of a model, that it is giving those results. So, for understanding that, model reliability is one of the things which we need to understand first. Uh, the single train test which we are actually doing in many of the cases is misleading. It can be misleading, definitely. So a single test split may sometimes overestimate, or it may underestimate. It sometimes may overestimate a performance, sometimes it may underestimate a performance. There can be a cause that you are getting, for example, false coincidence in your model. So all of these, I would say, apprehensions are there, but these are some realistic concerns as well. So robust evaluation method, that is something which is very essential, and you should be trusting the model quality, and then only you will be able to implement it in a very critical situation, a realistic situation, where the performance of a model will be very critical. So there are certain scenarios, we have given examples of those scenarios as well, in which the model performance is very critical. Even a minor degradation or decrease in that can have serious implications. So coming back to this model reliability, that means this is very important and we need to ascertain it. So first thing what we are having is, I'm introducing a concept of cross validation. First of all, what is this cross validation? Cross validation replaces the single train test split approach with multiple splits. So it is not a single train, as we have seen and witnessed in most of the cases before, that it's a single train test split. So we are having single test and a single test data, single train data, on which we are doing a split, and then based on that, the machine learning model is deciding. But in this case, when we are having, cross validation, we are not estimating it like that. So we are providing a more reliable estimate of the model that will be, will perform on unseen data. How your model will perform on unseen data, that is, something which will be, in fact, when it will be a single train test supplet, it is going to be a concern. But when we are having multiple, so definitely it is going to have an enhancement. So multiple data splits is first thing which we are having in this cross validation. A reliable performance estimate, so that is one more thing. And multiple exam analogy, there's in fact an analogy with this multiple exams that I'll be in fact providing you definition of that. Analogy is like, it goes like this, I'll be giving a definition when we reach to that slide. But analogy in a very gist is that, like if you're giving one paper to a student, it might be coincidental sometimes that student performs very well. So that is, it can happen once. But if you're testing same student multiple times with different papers, it is very unlikely that he'll be getting lucky every time, and it is very unlikely that every time it will be a coincidental thing that he's until and unless student is realistically performing in that consistent manner. So that analogy fits here as well when we are talking about cross validation. What happens in cross validation actually is, so we are saying k-fold cross validation. What is this k-fold cross validation? So let us take the example that k is equivalent to 5. So what happens is data set splits into 5 folds. So each fold, data set is splitting into 5 folds. So we are having each fold test once. So every fold is testing once. Average is equal to, and then on the results, when we see the average of all of those which have been provided is a final result. So the cross validation analogy, which in fact I explained to you in a gist, the student exam metaphor. So what is this? A single exam paper can be too easy or too hard, giving an unfair score. Multiple papers provide fairer assessment of true knowledge a student is having. So cross validation works the same way. Multiple tests yield an average score. So like you'll be able to see cross validation how it's working. Like we will be able to ascertain the realistic performance of a student by giving multiple papers, and if it is a consistent performance by the student, we will just say yes, a student is realistically meritorious or consistently performing. It is not just a one incident, isolated incident that student has performed well, bad or good. It can be both the cases. So in the same manner, we can just see when we are cross validating a model, so we can just see how it is performing in a consistent manner, and the average of that can be taken as a realistic performance then. So k-fold mechanism, in which we have taken 5, k is equal to 5. We can have a fold 1 on which we can train on 2 to 5, and 1 can be taken as test. That means the data which is a fold 1, it can be taken as a test data, and we can train it on from 2 to 5. In the same manner, we can rotate it then. That means 2 will be taken as a test data and rest of them will be taken as train data. Then 3 will be taken as, so it will be rotating. So average for final results, then what will happen is we'll be getting average for final results. So this is in very just what k-fold mechanism is. So cross validation, if you just see one example, and I'm just going to implement this and I'll be showing you one example in Python itself now. That Python implementation using sklearn's cross validation score function evaluates models performance with 5-fold cross validation on real data. We are loading the breast cancer dataset from sklearn, a dataset that we had done in the earlier program as well. And then with 100 estimators, that means we are having decision trees, 100 of a random forest classifier. We are having cross val score model echo k. This is to run 5-fold validation. So we are running this 5-fold validation, and then we are printing the individual scores and the mean accuracy. So at this point in time, I would like to stop here, although there are certain more things which we need to discuss. But if you just see here, I would like to show you this program which is on cross validation. This is cross validation example, simple and clear. This is in fact loading importing data from different libraries. So that is happening here, train test, and that we are importing from sklearn. And then iris is also there from sklearn. Then we are having decision tree classifier and numpy as np. So all of this, and then we are making the initialization. So data is equivalent to load underscore iris. So we are putting that into data, and then x is equal to data or data, okay, features, and data or target, it means labels. We have loaded that into x and y, and then we are putting the decision tree classifier. You just see model is equivalent to this, and then exactly we are putting a train test supplet, which is there. Now, normal approach we are taking, and this is the normal approach which we are having, and then model fit. So then accuracy is equivalent to. So here we will be checking what will be the accuracy of the model if we are putting it in a normal way. Okay. So what is going to be the accuracy of this? Now we will be having cross validation for this. So this is a normal way how we had been doing it, in fact, in random forest classifier earlier as well. So this is a normal way. Now we are changing it to cross validation. So now I am saying cv underscore scores is equal to cross underscore val underscore score. So then model x, y, and cv is equal to 5. So I'm taking it that now cross validation will be 5. So print cross validation scores cv underscore scores, and then it will be giving the mean average of these scores, and then it will print what is the main score. That means what will be the final result here. And then with this one, we will be able to see what difference does this cross validation give us. So let me just go to a run, and I will click on this run without debugging, and I'll say Python program, okay, uh, without debugging. And then it is now, because it took some time, in fact. So train test accuracy is 1.0, cross validation scores 0.9667, 0.9, 0.9, and average cross validation is 0.96. So it is giving us if you just see here on this one, it is giving us in fact an exact performance of a particular machine learning algorithm. Because otherwise, if we are running it in a single this one, it is showing us accuracy which is on the higher side as well. So as I told you, this cross validation is not for one side of the picture only, that it will be giving us less results or something like that. It is both sides. It might be a performance which will be 100%, but realistically it won't be 100%. It will be something else. So when we are taking average of this is the model is performing very well. But if you just see average scores which are there with cross validation are 96. So it's not 100%, it's 96%. So then we can have different scenarios in which cross validation can have a significant impact when it comes to checking and evaluating the exact performance of a machine learning algorithm. And this example, a very simple example, very small example, although, but it is very effective in fact in ascertaining that. So with that, I am just going to stop it here. I want to just keep these videos little short. So we're having a lot of concepts as far as this is concerned. I want to just because most of the videos which are there in this particular series, they are 20 to 25 minutes, but it's a good practice to keep the video short. I hope that this cross validation with the practical implementation in Python, you would have got it. And thank you so much once again for joining us, and then give your critical feedback so that we can improve, and we'll be able to provide you better content, which will be in fact resulting in some contribution to your overall knowledge and clarity of concepts, especially in this particular series related to machine learning. Thank you so much once again for joining.